Is it better now? Oh, maybe someone can adjust this. Good. Yeah, so maybe first I should clarify what do these two works have in common and where do we diverge. So in general, we are both interested in strengthening proof techniques that are inspired by the classical notion of a ranking function. And I think although Annabelle did not mention this word in her talk, it's basically hidden somewhere under the hood. So to recall, in its simplest form, a ranking function for a classical non-probabilistic program is some function mapping program states to, let's say, real numbers, such that the value of the function is bounded from below, let's say by 0, as long as the program continues executing. And at the same time, in each step of the program's execution, the value of the function should decrease by some constant, let's say by 1. And of course, an existence of such a function for some program shows that the program cannot execute forever and must eventually terminate. And this has been previously generalized to probabilistic programs, and the generalization basically proceeds by replacing this deterministic decrease condition with a probabilistic analog, which means that whenever we are in some state where the function has some concrete value, then the expected value of the function after making one probabilistic step of execution from the current state should be smaller than the current value, again, let's say by 1. And this is also known as, this function is also known as a ranking supermartingale. This is what Annabelle recalled in the beginning of her talk. And she also showed some examples of programs that cannot be, that do terminate almost surely, but that cannot be handled by such a proof rule. So the motivation is to strengthen it so that it works for a larger class of programs. And where I think our works diverge is that we sort of aim at different classes of programs to be handled by the new proof rule. And in our work, we are in essence interested in programs that might go through several different phases of execution before termination. And due to this sort of complexity in behavior, they might either not admit a probabilistic ranking function of this form, or they might admit it, but it might be too complex to be computed automatically. And to solve this, what we basically do is that we generalize lexicographic ranking functions, well-known classical notion, to probabilistic programs. So these are our main results, and the core result is really purely mathematical. We introduced a notion of so-called lexicographic ranking supermartingale, and then we prove that these Lex RSMs, for short, provide a sound proof rule for almost sure termination of quite a general class of stochastic processes with non-determinism. And then we apply these results to program analysis, and we show that in particular, Lex RSMs can be used to prove almost sure termination of probabilistic programs, again with demonic non-determinism, and that this proof technique can be actually efficiently automated. So we have some prototype implementation, some algorithm which generalizes an existing classical termination proving algorithm. And these Lex RSMs have also other features related, for example, to compositional reasoning about almost sure termination, or to obtaining bounds on expected runtime of the program, but maybe let's talk about this later if there is time. So let's dive into a bit more detail. And I've mentioned the main result is basically mathematical, but I will present it in the context of a very simple model of probabilistic programs. It's very similar to the model that Annabelle worked with. So we have simple imperative programs with numerical variables. It has standard programming constructs, of course, including loops. And we have two types of probabilistic constructs, which is probabilistic branchings and sampling of a variable value from some probability distribution. And just I will mention that we allow both discrete and continuous distributions. And yeah, as mentioned, we also have demonic non-determinism in both branching and assignments. So let's have a simple example. This will be a running example for the talk. It's quite adaptation of a very classical example from termination proving literature. We have two variables, x and y. The loop terminates as soon as one of the variables becomes negative. And inside the loop, we have a non-deterministic choice. And we either probabilistically decrease the value of x. And here, the expected magnitude of this decrease is by 1. This is like the change is sampled from a uniform distribution over this interval. Or we double the value of x, but in that case, we probabilistically decrease the value of y. So we have some sort of random walk mixed with this non-determinism and something else thrown in. And our task is, when we are given program, let's say like this, we want to prove that the program terminates with probability 1, no matter how is this non-determinism resolved in each iteration. So how can we do that? One possibility is to use this classical, or I think already classical, simple form of a ranking supermartingale. I call it one-dimensional ranking supermartingale because it maps program states simply to numbers. And indeed, this program admits such a ranking supermartingale. It has this form. I'm not doing the computation here, but indeed, no matter which path through the loop you take here, it holds that each iteration of the loop decreases on average the value of this expression at least by 1. So that's fine, but what is troubling is that this expression is first nonlinear. Actually, you can see that we also have an exponential term here. And of course, this is not so good because then it might be hard to actually automatically compute such a, let's say, almost sure termination certificate. Because from various application domains, we know that automated reasoning is much easier over linear arithmetic than over nonlinear one. And of course, this is the point of the example. It was constructed in such a way that it admits no one-dimensional function of this nice linear form, linear in the program's variables, that would prove almost sure termination. So what can we do instead? We can basically generalize the tool that resolves similar problems in the classical setting, and that is we generalize lexicographic ranking functions to probabilistic programs. And we call these lexicographic ranking supermartingales. So we now have a function which maps program states to, let's say, real vectors. And first we require that, again, that there must always be some lower bound condition that the value of the function is non-negative in each component as long as the program keeps running. And again, we take the classical lexicographic decrease condition and replace with probabilistic analog. So let me just rephrase this paragraph. So the function must satisfy the property that for each reachable state sigma, when we look at the value of this vector function in this state sigma, and then we look what is the expected value of this vector function after making one probabilistic step of execution. These are both vectors. Then this expected next value must be smaller than the current value in a lexicographic ordering. Fine. So there is nothing that much surprising here. This is very straightforward, I would say, carryover from the classical setting. What is the tricky part is actually proving that this sort of ranking function works for proving almost sure termination of probabilistic programs. So the main result of the paper is really this soundness theorem here. And when proving this result, one really has to avoid certain pitfalls and intricacies. And I would like to mention a couple of them because I think that they are quite instructive about what is going on in this probabilistic world. But first, just to conclude the tangent, let's get back to the running example. Of course, we have a two-dimensional and nicely linear lexicographic ranking supermartingale for this example. So either y stays unchanged and x decreases by 1 on average, or y decreases by 1 on average, and we don't care what matters to x. So again, this is the same as in the classical setting. So now, how about, so what are the intricate parts? So one interesting thing is that in the probabilistic world, we have much less freedom in choosing this lower bound condition in the definition of this lexicographic ranking function. So of course there must always be something that basically in the classical world we would say something that makes the transition relation well-founded. And so in our paper we proved that this concept of lexicographic ranking supermartingale works. It's sound for proving AS termination if we require that all components of the function are non-negative throughout the program's execution. But again, in the non-probabilistic world, people have come up with the alternative notions of this lower bound. And for instance, on the, let's say, more liberal side of the spectrum, what is sufficient is that for each transition of the program, we look at what is the leftmost component of the vector function which is decreased by this transition. And in this concrete step, this leftmost component must be bounded from below. And this is perfectly correct for proving classical termination. But in the probabilistic world, this completely breaks down in the sense that there would be now programs that do not terminate at all. They would terminate with probability 0. There would be, of course, probabilistic programs. And they would still admit this sort of termination certificate, so lexicographic RSM with this sort of lower bound condition. Of course, we don't want such an unsound proof rule. There is also some sort of intermediate notion of this lower bound condition, which we have not investigated into much detail, and I believe that this one would lead to a sound proof rule. So this is an interesting thing to look into. Okay, another thing that can basically happen only in the probabilistic world is that when for example, when we want to prove the correctness of these lexicographic RSMs and we are doing computations with these objects, then what can happen is that quantities of infinite expected value pop up during the computations, which somehow makes things harder. And this can be illustrated on a nice simple example, which was again taken from some previous literature where it was used in a bit different context. So here we have simply two consecutive while loops. And the first while loop is such that the amount of the number of iterations we spent in this while loop is geometrically distributed, because we basically wait for the first time when C is set to 0, and this event is controlled by a fair coin flip. But at the same time, in each iteration of this loop, the value of x is doubled. And this means that the expected value of variable x upon exiting this first loop is infinite, right? Because it's equal to 2 with probability 1/2. This corresponds like exiting the loop after the first iteration, to 4 with probability 1/4, and so on and so on. And this sums up to infinity. Now in the second while loop, we simply deterministically decrease the value of x. This program does terminate almost surely, because each individual loop also terminates almost surely. But what is interesting that the termination can be proved, for instance, by using this simple linear Lex RSM. And note that the value of this variable x provides one of the components of this Lex RSM. And this shows basically two things. So the first thing is that when proving that these Lex RSMs provide a sound proof rule, we cannot really look just on expectations of these components, because here at this point the expectation of x is infinite, and how do you prove that something of infinite expected value eventually decreases to 0? So what we need to do instead is to do some more precise bookkeeping of distributions of these individual components. Another thing to mention is that this program actually terminates in infinite expected termination time. infinite expected number of steps because the expected amount of steps spent in this second loop is infinite. And so this basically means that Lex RSMs provide a stronger proof rule than these one-dimensional ranking supermartingales, because again, it was previously proved that whenever a probabilistic program admits a one-dimensional ranking supermartingale, it must terminate in finite expected number of steps. Okay, but this also begs another question, and this is whether Lex RSMs can be actually used to obtain some bound on the expected runtime of a program. This is often the feature of various ranking artifacts, and we would like to have it as well. And the answer is yes, under some additional assumptions. So we basically have a theorem which says that when you are able to find some linear lexicographic ranking supermartingale for your program, which satisfies a certain technical property, whatever that means, bounded expected conditional increase, then the existence of such a function proves that the expected runtime of the program is bounded by a polynomial. And basically, both the degree of the polynomial and the coefficients, which are hidden by this Bicot constant, can be inferred from the Lex RSM. So this condition is somehow technical, but in its core, it's simple. We basically require that whenever a step of execution is expected to increase a certain component of the function, then this expectation of the increase must be bounded by something which is independent of current variable values. So this is basically something that would be very easy to prove in a classical setting, but again, for probabilistic programs, we need to do a bit more involved computations. Okay, couple of words on experiments. So we generalized one termination proving algorithm for classical programs back from 2010s, so that the generalized algorithm works with probabilistic programs over linear arithmetic and looks for or checks the existence of a linear lexicographic ranking supermartingale of an arbitrary dimension. And so this algorithm back from 2010, it's one of these types of algorithms that basically require that you provide it before you run the algorithm, you need to provide it with sufficiently good linear invariance for the program. So basically, by this I mean some linear over approximation of the set of reachable states. Otherwise, the algorithm might fail to find this ranking function, although there might exist one. So what we did some simple proof of concept experiments. This is not meant to be like some practical toolchain, but we implemented this generalized algorithm and paired it with tool ASPIC for invariant generation, which is basically by the same authors as here. And we experimented on two kinds of benchmarks, and I think maybe probably the more interesting lesson is from the second set, where to get some idea on how might such a tools or such an approach scale, we experimented with some synthetic benchmarks where we sort of artificially created larger and larger programs, and kind of the threshold up to which it scales well was something like 10,000 lines of code. And then it starts, really, the time explodes, and the bottleneck is this completely non-probabilistic step of invariant generation. So, of course, that's also not very surprising because invariant generation is, in general, expensive. Okay, so this brings me to the last slide. So again, just to recap, our main contribution was this mathematical notion of a lexicographic ranking supermartingale and proving that it is sound for almost sure termination of probabilistic programs. But there are other features of this, and you are welcome to either talk to me or to read the paper to know more about this. But the last question I would like to pose: what to do next with this? And I think. If you remember the previous slide, I've mentioned that now we are using this quite straightforward method where you need to upfront compute as good linear invariance as possible, and then you run the termination checker. But Again, if I look for inspiration to the classical world, then there people are using something more clever, right? Basically, what is sort of state of the art is reducing the termination checking to some sort of iterated safety checking, and in this way you only need to compute invariants that are actually needed for proving termination. And in the classical world, there are basically two ways of doing this, either via disjunctive termination proofs or by using lexicographic ranking functions. And I think it would be really cool if we had some similar method in the probabilistic world. And yeah, it's not clear how to do that. There are more obstacles to overcome. But at least now we have one of possibly useful components for this, and this is the notion of a lexicographic probabilistic termination proof. Thank you.
So let's thank the speaker. So if there are any questions.
Hi. Have you looked at synthesizing polynomial lexicographic supermartingales?
Not yet. So I mean, some of my colleagues and previous collaborators, they looked into polynomial ranking supermartingales, but only one-dimensional ones. That was, I think, like previous year or 2 years ago. But I personally am not much aware of this.
The second question is, would it make sense to then try and combine the two approaches that were just presented?
Which two?
The ranking, the lexicographic one with the martingale approach?
Well, definitely yes, because in principle, each component of this lexicographic ranking function is basically something like a one-dimensional ranking supermartingale. We just allow it to sort of cheat if there is some previous component which works, right? So yeah, of course, it makes perfect sense to try to substitute some other notions for this.
Okay, are there other questions? Okay, if not, let's thank the speaker.